行了，等一下
Jerry
再说
and
吧，
Louis.
我现在要开会。好，好吧，好，好，没事。
First off, I'd like to thank everyone for coming out here and taking your time away from this beautiful day to come see our presentation. My name is Stephen Compy. I'm the project manager.
My name is Louis Salazar. I'm a computer engineer.
William Yapis, electrical engineer.
My name is Luis Gonzalez, computer engineer.
I am Sherry Quesada.
And together, our capstone project is two birds, one capstone. Here's the outline of what we're going to be talking about. We're going to be going through an overview of the project, how it's going to affect society. We're going to talk about originality, and we're going to go into nitty details about our project. We're also going to have a case update. We're going to talk about our laser case, our risk analysis, our budget report, and our results. So, what our project is. Our project is an entertainment game. Two drones are going to fly autonomously, and the shooter is actually going to have a hand-built laser gun. The whole point of this is to shoot the drones with the laser, and we'll have a level system in place with the final level being shooting the two drones with one shot. The drones that we used are co-drones, and we use them because they're small, they're light, they're programmable, they have sensors and receivers. Our laser concept was using a laser diode channeled with a PVC pipe that would shoot out. Overall, these designs had to change due to the unexpected problems that we faced during the semester.
So our drone, our game, had a society impact. Currently, shooting games are becoming more popular, so such as competitive shooting has become a really popular sport in high school. And studies believe this gain in popularity has to do with students' inclusivity, so inclusivity such as people with disabilities, such as people with wheelchairs. So people in wheelchairs will be able to shoot, are able to participate in shooting games. And you don't need to be athletic to shoot a gun. How this can impact shooting games. Shooting lasers is a safe alternative as opposed to shooting as guns, obviously. It's more resourceful and environmentally friendly. So there's no waste, as in like there's no bullet shells, there's no clay targets, it's all spread out all over. And the laser and drone are reusable, so they're environmentally friendly. We split up into two groups, three groups, the laser team, the laser gun case, and the drone team. The laser team was the electrical engineers took care of the laser. The laser gun case was by Stephen Convey, and the drone team was consisted of the computer engineers. And once again, the electrical engineers are William Yapis, Stephen Convey, and I. The computer engineers are Bruce Gonzalez and Louis Salazar. The originality, we did some research on patents that were some patents that were out there, and we found a similar patent. There's called the Duck Drone LLC's targeting system. As you can see here, it has a master controller, which would be the gun, and our standard the gun, which would be the gun, and then you see the drones here, and similar to our project, but our focus is solely on recreational uses, and our goal was to have collateral shots of drones, but as we will explain later in the slides, that was not our final product.
This is our first laser. We started doing this during the first semester. So this is supposed to this works with the drone to shoot the drone. It's supposed to work, but later we found that there was a problem with it. So the problem, after we needed to do some research, so we called the company and we tried to find out what was the problem. And we found out that there was a problem with the frequency of the laser. It has to have a specific frequency for it to work. And we needed 40 kilohertz for it to work, or else the drone wouldn't recognize the laser.
This is also a simple design. The whole purpose of it is to activate a laser diode that was channeled through a PVC pipe that was attached to our laser case.
So we needed to make a new laser that has the 40 kilohertz. So we started doing a second one. We added a few bars, and also we added a safety mechanism, a fuse, just in case we went over current.
Within the design, we used the Allen 555 and a 5-volt power supply. We tested and simulated our design, as you can see.
So this is the simulation of the laser. In the left you can see the BSPI simulation, and on the right you can see the real life simulation that we tested with an oscilloscope. To get the numbers to match 40 kilohertz, we use the equations on top to get the frequency and the period that was required for it to work.
We did some laser frequency documentation, so we did testing to find the frequency that we needed, which was 40 kilohertz. So this testing consisted of changing the resistance values and being able to get the frequency to as close as 40 kilohertz as possible. So we tested it 5 different times. We have our first resistance values were 2K and 620 ohms, 2K at 560, then 2K at 510, 2K at 470, and then 2K at 390. As we lessened the second resistor, it came closer to 40 kilohertz. So at first it was at 38, then 39.1, and 39.9, which was our best result. And that was our best result.
So looking into the drone itself, we were able to replicate the laser at which the sensor can actually read the 40 kilohertz frequency. But unfortunately, within the firmware of the drone itself, the IR laser has to have a message within it that it could recognize as a team as they'd have it set up. So to get around this, we actually had to dismantle one of the drones and use it as a laser.
So as Bruce explained, unfortunately, because of inside the header file, they specifically said only these messages could be received by the drone. We were unable to replicate that signal, unfortunately. So we had to switch to using the drone. We had to dismantle the drone, we had to put it inside our case and use it. So now that we were decided on using the drone, we now had to test the limits of our laser now. So we made these two codes. The first is a shooting code. All it really does is every second it shoots the laser out of the gun. And the receive code. The receive code is also pretty simple. Basically, the shooting drone hits the receiving drone, and it makes a sound on the controller, and it changes lights on the drone itself. In order to test the distance it goes, basically what we did is we incremented the range. Basically, put the two drones right next to each other, and we incremented the distance between them by 5 feet until we hit 20 feet. At which point we didn't get a signal anymore, and then we decremented by 1 foot until we got a stable connection. Note that at 18 you could get a stable, you could get a connection, but unfortunately it wasn't reliable, so you have to go that step.
So we wanted to get the max speed of the drone as well. To do this, we ran a couple of tests and trials. We had 4 members run timers on their phone while we had another member control the drone to move the desired motion, whether it be lateral motions, horizontal forward, or an acceleration up. After running each direction 5 times, we came up with average max speeds. And all our standard deviations were under 0.3, so we were happy with our times, our measure of error, and these are the results. As well as speed, on top of speed, we needed to take into account any offset from drift, because it's not an ideal world, as well as motors are different. Sometimes a motor can take the same amount of voltage and spin a little faster than another motor. So to do this, we actually have to trim the drone. And trimming actually updates any offsets within the firmware of the drone, and it'll stay in the drone until any changes are made within it. And there's 2 ways of going about it. You can either hard code it within your coding, which is an example of right here, where we put a trim on the roll, which would make it move to the left to offset any right, as well as a throttle, which would make it stay up as opposed to falling down. And another way that you can do it is actually incrementally through a controller, have it adjust to any drift, so you can have the drone take off. It'll hover. If you see it moving in any direction, you can offset it, and that'll actually update within the firmware and cancel out any offsets in the future. So we ran some testing. We had the drone fly up for 10 seconds, hover, and land on that pad. At first, we ran this 5 times. At first, our average displacement was about 32 inches, which is significant. We do not want this in a shooting game. The drone could fall off, like off a table, possibly, or something like that. So we added our trim. After a lot of trials, we were able to get it down to an average of 6.02 inches after 5 trials, which is a significant increase. We were happy with the results.
So this is our case design. We made the program we used was NX, which was NX is a 3D modeling software, and we had multiple designs. So our first design was made for the custom circuit design we had built. But after we figured out that we needed the IR diode needed a specific message through the laser itself, we changed the design so we'd be able to fit the drone itself, the Arduino, and the battery pack. So this is what we designed on NX program, and this is our result. The PVC pipe is there because from our previous design, like I said before, like Steven said, we were going to use a laser diode and a lens to actually so the PVC would be able to be used, but unfortunately we weren't able to use that.
The standards we're using this are the Z136 standard, which is basically the indoor laser standards. Make sure that the laser is not harmful to anyone's eyes or skin, anything like that. As well as the Bluetooth standard, which we use for the connectivity between the Arduino board and the drones. And as well as for our original design of the laser schematic, we use a National Electric Code to make sure that all those circuitries were safe. And then finally, we use the FAA regulations for the drone to make sure max velocities and dynamics on the drone were set to the standards that were required.
So during our project, we had to take some variables into account. First variable was that the laser that we made might not actually interact with our drone, which is a real possibility. And our backup for that was to obviously use the drone itself, or to transmit the laser itself. Another problem that we had was the autonomous code might not be compatible with the drone we're trying to use. Unfortunately, that wasn't the problem, and the only solution for that was to use a different drone. Our drone itself is really light. It's not more than a couple pounds, and so basically playing it outside would be impossible because any wind shifted over to the right or to the left. So our solution to this was to make it an indoor game as opposed to an outdoor game. Bluetooth interference was a bigger problem in our project because especially in these buildings where we use 2.4 gigahertz bands, basically trying to connect more than one drone at a time was pretty difficult, and it would take up to 5 to 10 minutes in order for the second drone to try to connect. In order to offset, we would like to use Bluetooth. We like to use Wi-Fi instead of Bluetooth. Another problem that we had is that for our original concept, we wanted to have 2 drones flying in the air, and we had to avoid both drones. And then the solution for that is to trim the drones. Unfortunately, we didn't get to that point due to constraints. And one of our biggest problems was the battery power. Once these drones start to go low on power, they start to sway a lot. They go the motor speed start to reduce and go down to the ground. And our solution to this was to have a lot of batteries available in which for us to exchange the batteries while we're working.
We were happy to see that we stay under budget. We had a budget of $200 and we only spent $122.79. That's with all the parts. What really helped is to stay under the budget is that we also bought the 2 drones for ourselves. It came out of our own pocket. So we were happy to see that we went under budget.
And as you can see from this part list, a lot of these stuff are things for our homemade laser. Unfortunately, we didn't get to use all this stuff because we had to alter our design.
Alright, so in order to show our proof of concept, we made a pretty simple design, a pretty simple code basically. The drone would fly up, the user would try to shoot it, and it would come back down. As you can see, we can tell that the drone was able to go up. The user was actually able to shoot it right down. But that wasn't enough for us. We wanted to also a more complex design. We wanted the drone to move around, and we wanted to make sure that the user was able to shoot it while it was moving. As you can see there, the drone made a couple circles, and then Steven was able to shoot it out the air using the gun pretty easily. So we have our proof of concept there.
Here is a list of our works cited for our research that we've conducted, such as like looking into patents, standards that we used, and basically anything that's like this. Finally, would like to thank Dr. Wayne, Dr. Hussein, and Dr. Ryan for all the help that they've given us, and overall the entire EEC department for all the help that we were generously given. Any questions?
Did you guys have any other alternatives than the diode and the PVC pipe for shooting the laser?
Yes, our other alternative is we actually used the laser that was in the drone. So, and we were able to retrofit it with our laser case that we built to actually work like the laser that we wanted to. And it was shown in the diagram. Any other questions?
Okay, thank you.